Have you ever wondered how machines learn? Join us on this short recap to see how machines learn gradually with the concepts of reinforcement learning. What is reinforcement learning? Well, you can think of it as a point where humans learn by trial and error technique. For example, do babies learn to walk on their first attempt? No, right? They try, fail, try again, and repeat the cycle for a duration before they start to walk. Interestingly, the process is the same with machines too. So let's find out how this phenomenon occurs in the real picture. Reinforcement learning focuses on teaching agents through trial and error. It learns by actively engaging with an environment. The building blocks of RL are based on 4 fundamental concepts. First, you have an agent who resembles you. This agent can perform actions similar to the way you do things. These actions are performed in a given environment. Just like in real life, you can observe the environment the agent performs and reward for the actions. The agents can continue to learn from mistakes and improve. Doesn't it sound interesting? Let's find out. Reinforcement learning can be implemented in different ways. Deep Q learning is a common method used here, where you have a neural network to take inputs for processing. The environment around you is called the state, which is also the input for the neural network. The neural network processes your input and suggests the best possible option that you can take. You can gradually improve the neural network based on the rewards for performing a particular action. The end result of this is an agent that learns through trial and error. Now let's start our experiment with an agent. Suppose we have a rectangular room with 4 walls and a target. Our agent needs to self-learn to reach the target without hitting the walls. The agent can move from one state to another by going up, down, left, or right. However, before making any movements from one state to another, we feed the agent with some hints. To start off, let's tell our agent where the target is for the agent's current position. Also, we will say to the agent the direction it is moving forward. Now that we have set up the environment, it is time to find out how to build the reward function. This is another way of saying whether the agent has done something good or bad during each instance. Each time the agent moves from one state to another, we reward or penalize the agent and set some rules. If the agent collides with a wall, the game is over, and we reward negatively. Similarly, if the agent moves away from the target, it indicates that the agent does not adhere to our requirements. Therefore, we reward the agent negatively. If the agent tries to reach the target, it is a good sign because the agent is making an effort to comply with our end goal. As a result, a positive reward is awarded to the agent. Furthermore, to take another step ahead, we need to make our ultimate goal to persuade the agent to reach the target somehow. Therefore, if it reaches the target in some way, it should be rewarded more. To do this, we award a higher positive reward to the agent for reaching the target. Our reward functions are concluded here, and it is time to see how the agent acts in an implemented environment according to our reward scheme. We trained the agent for more than 200 episodes, and this short video shows how the agent gradually learns by itself with time. Initially, after training for just 1 episode, you can see that it fails to reach the target and ends up colliding with a wall more often than not. After 20 episodes, it has learned a bit, and we can see some improvement. After training for 180 episodes, you can see how it has learned itself and how the agent reaches the target more often. Since the agent learned to find its way toward the target, we decided to make life difficult for the agent by adding an obstacle in the middle of the grid. However, we also increased the set of things that the agent can sense. The reason, we expanded the number of elements in the input space from 8 to 27. We also upgraded the agent by giving it more freedom to move. Previously, the agent could only move toward the top, bottom, left, or right. Now, while moving towards a particular direction, the agent can walk a unit distance while taking a left or right turn up to 90 degrees on either side. In addition, to simplify the process, we have restricted the angle of direction to be in multiples of 10. Now, after each state, the agent can take 19 actions and, more importantly, walk with more freedom. Suppose that the agent decides to take a right turn of 90 degrees. Then, this is what effectively happens. Similarly to the previous implementation, the agent learns with time, and with its newly given freedom, we can now see smoother movements from the agent. After being trained for just above 5 episodes, it is clear that the agent struggles to achieve our goal. It collides with either a wall or an obstacle more often than previously. After 300 plus episodes, the agent has learned a lot about avoiding obstacles. Of course, on rare occasions, it collides with the obstacle, but it clearly reaches the target more often than not, and this is a big improvement. After 650 episodes, the agent has improved even more, and you can see how its mean error rate has decreased over time. The agent sometimes travels nearby the obstacle, but it tries its best to avoid collisions on its way toward the target. Next, we decided to make it even more difficult for the agent. But how will we make life difficult for the agent this time? A good way of doing this is to add a grid of obstacles for the agent to crawl through the obstacles on its way towards the target. Will it succeed? Let's find out. Let us see how the agent fares in this more complex yet exciting environment. We trained the agent for a few hours, and you can see how it has improved as we progress through training of 10, 800, and 1375 episodes. Just like we expected, the agent gets more competent from episode to crawl through the obstacles to reach the target. Despite traveling long distances while avoiding obstacles, the agent performs an excellent job of eventually reaching the target. It's fascinating to see how the agent learns to reach the target by itself without colliding with obstacles. But, more importantly, the agent is the one who decides the best possible action to take before each step. This was a simple demonstration to show one of the many ways how machines learn from data. If you are interested in learning more about this, refer to the link in the description to get more insights on this model of reinforcement learning. Enjoy!